Welcome everyone. Today we are going to talk about operating global scale Prometheus deployments on Kubernetes. I'm Orcun, principal engineer at AWS, focusing on open source observability solutions.
And I'm Alan. I'm also software engineer at AWS and a Cortex maintainer.
All right, we have a lot of challenges operating at global scale. And on the bottom right side, you can see a post-it that I prepared when I joined the team 2.5 years ago about the challenges we had back then and a priority order. We are not going to talk through every single one of the problems and challenges, but a subset of the challenges are going to act as our rough agenda today. We're going to touch base on availability, multi-tenancy, blast radius reduction, operating at global scale, and Kubernetes complexity. Before we dive in, let's rewind a bit. Let's talk about the ecosystem and how the ecosystem has evolved. So in 2012, Prometheus was started and then open sourced in 2015. Cortex project, a Prometheus-compatible, scalable open source project released shortly after. And we released Managed Prometheus by Amazon at 2020. We wanted to take away the operational burden of handling the infrastructure from the users. We have an open source first tenet. So any improvement that we do, we contribute back to open source community. And you can see that from our commits over the past 2 years in the Cortex repository. So before we launch the service, let's go through what we wanted to launch back in 2020. We wanted to provide a fully managed, serverless, Prometheus-compatible monitoring service by AWS. That is scalable, highly available, integrated with AWS services, secure, supports IAM authorization as well as data encryption, and it can support data retention up to multiple years. As I mentioned earlier, we use Cortex under the hood, but let's talk a little bit about Prometheus. So Prometheus is an open source, purpose-built time series database that comes with a very powerful query language called PromQL. It enables analytical query capabilities on your time series data, but also integrates really well with Kubernetes, and it's widely adopted format and supports a wide range of exporters in the community. However, it inherently comes with limitations. The primary one that is our concern is that it's a single machine and it's deployed in a single machine. It's not a distributed system. It is a monolithic service. So depending on your use case, your use cases will be competing against the same resources in the host. Meaning if you have an ingest-heavy, write-heavy workload, then your queries are going to take a hit, or your alerting and ruler engine will take a hit. So there's no AZ redundancy whatsoever, and there are retention limits because your retention limit is basically going to be limited by the host's disks that you can attach to a host.
So, okay, as Orcun was saying, Prometheus, even though we really wanted to use Prometheus, it didn't fit our use case. So we kept looking around, exploring different solutions out there, and we end up picking Cortex. What's Cortex? Cortex is a CNCF project. The main proposal of Cortex was breaking down this single process solution that's Prometheus in several microservices. Each one of those microservices would have a very specific role in a Cortex cluster. And what's good as well is that Cortex uses Prometheus code base under the hood. So Cortex imports Prometheus as a library, and this makes easier for Cortex to be fully compatible with Prometheus, and also is easier for us to backport new features that Prometheus is developing, such as like native histogram lately. So this is a very high-level view of a Cortex architecture and how the components interact with each other. We are not going into details of what each component does. We had talks about that in the past already. But the main thing here is that we have basically three paths. We have the write path in red, which includes distributors and ingesters. We have the read path in blue, that includes the store gateways, queries, and query front-end. And the alerts and ruler path in green, that includes the alert manager and the rulers service. OK, Cortex not just break down Prometheus into different microservices, but also allow us to scale those microservices horizontally. This means that in a Prometheus setup, we are not bounded by the size of a single host anymore. I can scale my fleet to handle more traffic as the traffic increases. Also, having those different microservices gives us lots of flexibility in how we scale our Cortex cluster. So let's say that if you have read-have workload, we can just scale the read path microservice, and those microservices will not interfere with each other. So there is some points of contact between the paths, but usually they are like the read path, the write path, and the alert rules and rules path are very segregated. Also, Cortex offer auto balance in response to any scaling activity. What that means is that we can scale our fleet, and Cortex will take care of rebalancing the load between nodes and resharding the data between nodes. And it uses under the hood consistent hashing, so we make sure that we have minimal redistribution of load when that happens. So scaling up and down Cortex clusters is quite easy. You can just basically go to a Kubernetes deployment, change the replica set. Cortex will see the new nodes, the nodes will register, and it will start receiving new nodes, start receiving loads. You can use simple things like Kubernetes HPA to scale up and down those microservices. Also, Cortex implements, it's built in on Cortex the concept of high availability. So Cortex implements high availability by replicating the data across nodes and AZs. And this, together with a quorum read, a quorum operation, means that Cortex cluster doesn't have any single point of failure and can tolerate hardware failures and AZ outages. Also, which was very important to us, is that Cortex supports multi-tenancy out of the box. Cortex keeps data from different tenants in isolation, so we don't share any data on disk between tenants. And also implements lots of noise neighborhoods mitigations, such as Cortex will give you limits and quotas by tenant to make sure that one tenant cannot use all the cluster resources. And also strategies like shuffle sharding, that is a strategy that we try to minimize the amount of resource shared between tenants. So in this particular case, we can see that, for instance, we have a bad tenant that's causing 3 hosts to overload, but the other tenants are happy because they don't share resources, and the one that they share, because of the redundancy and the high availability, the tenant doesn't have any impact whatsoever. Also, finally, Cortex supports a long-term storage. Cortex only keeps hot data on disk and ship this data every few hours to object storage like S3 or Google GCS. It means that we are not longer bounded by a local disk of a host, and this allows us to increase our retention period from days to years, which was something that our customers were demanding. OK, everything seems fine. Like Cortex is great, it's a good fit for us, let's go ahead. But we still have problems to solve. We don't want to have we don't want to have a single Cortex cluster that will grow indefinitely. We knew from previous experience that, like, especially in big distributed systems, we can have like very hidden scaling cliffs that only show up when the cluster gets to become too big. Those hidden contention points can show up in different ways. It can be some communication and coordination overload. And those things can cause also non-linear scaling, which means that you can end up, when you get to a certain level, certain size, you can end up adding more hosts, hoping to be able to handle more load. But the overhead is so big that adding more hosts is actually make things worse. Like the host is making you use more resources, and this can become a snowball effect. So we knew that we couldn't have like a single cluster for everything. So then that's when we started to think about cellular architecture. So in a cellular architecture, instead of having one single Cortex cluster, we have multiple Cortex clusters per region. Each Cortex cluster is now what we call cells. So instead of having one, we have multiple deployments of Cortex. And each cell should be self-contained. That means that it's not only Cortex that's deployed in this cell, but everything else that needs to run. Cortex needs to run. So like each cell has his own S3 bucket. Each cell has like the whole authorization and authentication stack. Everything's contained in one cell. And finally, we assign tenants or customers to cells. So we have every time that you create a resource in our system, we assign this resource to one cell and go from there. This gives us lots of positives. This means that we have more scalability, like we can always create more cells to handle more loads, to handle more clients. It improves our deployment safety because our deployment is now done by cell. So if for some reason we were shipping a bad code, instead of having that bad code run in my whole region, I will first run in a cell. If that thing has some problem, only the customers assigned to that cell will have a problem. Similarly, we have like a blast radius reduction. If for some reason Cortex could not protect himself and a tenant caused a Cortex cluster to get unhealthy, I have even more like isolation between tenants, because now this tenant can only affect one cluster or anything else. Like it can be like any type of disaster that causes the Cortex cluster to get unhealthy. Also, it decreases our mean time to recover, because like when we have an incident, the operator now can look to a subset of your fleet with a subset of your customers, instead of having to dive and like figure out your whole infrastructure. Okay, so a little bit about the cellular architecture. Like those are the main components that we have. We have a very thin layer called cell router. This layer is like the thinnest possible layer. That the only responsibility is take the request from the outside world and route to a cell. Like this architecture is hidden from the customer, so the customer has a single point of entry in our system that goes to the cell router, and the cell router will forward the request to the right cell. We have the cell itself, which is a Cortex deployment, together with everything else, as I said, that needs to be inside of the cell. So the S3 bucket, the authorization, the Kubernetes cluster, everything is inside of the cell. And we have the control plane. The control plane is basically responsible for administration tasks. It will like assign customer to cells. It will also provision new cells or deprovision cells if it's needed. Okay, a little bit about capacity management inside of the same cell. We keep the cells within a limit that we deem safe. And this limit, we get to this limit doing lots of different load tests and types of tests. And this is the limit that we feel comfortable of running a Cortex cluster. So every time that we will roll out a change, this change needs to be tested with a cluster, a pre-prod cluster, that is that's maxed out. That is like the size that we feel like that the max size that we can allow the cell to grow. So then we inside of the cell, we define two thresholds. One is called like scaling threshold, so which is the threshold that we set to stop assigning new tenants to a cell. And we have a hard limit, which is a limit that we don't want the cell to go above. So when you have like, so when all your cells are closer or above your scaling threshold, we scale out instead of scaling up a cell. What that means? That means that like we stop assigning tenants to that cells, and we scale out. We create a new cell to start assigning tenants to the new cell. Okay, but like what about the hard limit? How can we prevent tenants to grow inside of the cell and cross the hard limit? Well, for that we have some automations inside of the cell that allocate limits and quotas for customers. So basically how that works is we have like controllers that is like constantly looking at usage, customer usage, and it will auto-grant limit increases or give more limits to a customer, kind of outscaling the limit of the customer when it's deemed safe. So the controllers see like how much the limit was granted in this cell, and if it's below the hard limit, it says it's safe, you grant. This controller also reclaims limits that's not used. So if the customer was using lots of limits yesterday and stopping using, so we start to reclaim those limits to free up capacity to other customers. And finally, this controller also pre-provision nodes. When we create a new cell, we don't create the cell with scaled to handle the full capacity. So what we do is like we create a cell with a minimal footprint, and we let the cell grow organically. And when the cell is growing, the same controller, before granting limit because a customer needs, it will pre-provision nodes. When those nodes are ready, it will give the capacity to the customer. Okay, that works great, but what happens if a customer inside of existing cell needs more capacity? Well, in that case, we trigger an operation that we call cell migration. We create a new cell, or we pick a cell that has free capacity as target of the migration. We mirror this traffic between this. For some time, we mirror the traffic between the two cells. And this is to have same data in both cells. Then we start migrating configurations and historical data from one cell to another. Remember that even like the historical data is on a S3 bucket that belongs to a cell because we don't want any share between cells. So we need to migrate historical data. And then when everything's done at the end, we stop mirroring the traffic. I have all the data in the new cell, and I start to route also the read operations to the new cell. The customer doesn't note this operation. The only thing that the customer may note, and we are working to fix, is that in the end of this operation, the customer can receive some duplicated alerts. But other than that, should be totally seamless for the customer.
All right, so you might be wondering, how do you release all of this complexity to over tens of regions, hundreds of cells, and clusters across tens of thousands of hosts? So what we do is what we call deployment waves. In our deployment process, we want to release every change safely, but we want to respect the cellular boundaries as well as regional boundaries. In our pre-production steps, we run our unit tests and make sure that everything is passing, and then we deploy the new change to our what we call beta environment. And in our beta environment, we run our integration tests, etc. And if everything looks good, we start what we call production waves. Each wave consists of multiple region deployments. As the big waves you can see up top. We pick a rather small region to begin with, our deployment process. And each wave consists of subwaves. In the subwaves, we start deploying our change to our gamma environment first. In our gamma environment, you will realize that we deploy our changes to 2 cells to be able to test our changes in Cortex and also cellular router. And in our approval steps, as I mentioned before, we go through our integration tests. We have canaries running 24/7 in our gamma and prod environments. We wait for a few hours to get the signals from our environment and see if there's anything breaking with our changes. If there is, we look at what the issues are and then decide to roll back the change or we roll forward. In our first production wave, we pick a cell from a small region, we deploy our changes, we run our approval steps again, and in this phase, if we notice that if any alarms are firing, the system auto-rolls back the changes. So this is addressing one of the fundamental problems with the blast radius. So when we deploy a faulty change, we do not want to impact worldwide. We do not want to impact the whole region. Only a subset of customers and users are impacted by this change. But majority of the time, things are looking bright, and then we move on to our next phase. In the next wave, we deploy our change to the remaining cells in that region. We go through our approval process again. And then in the next big wave, now we pick 2 regions. Now that we have gained confidence in our first wave, we slowly expand the scope of our release. We pick the cells in those regions in gamma environment. We deploy our changes. We go through our approval processes again. And then notice that we pick a single cell in all these regions in our first prod wave. We wait, we see if everything's looking great, and then we move on to the next cells in that region. Notice that the subwaves and number of subwaves can increase depending on how many cells we have in the targeted regions. The process rinse and repeats to next wave of regions. We exponentially increase the number of regions that we deploy our changes to, and the overall deployment for a single change takes in the order of days. So a quick word about testing. As I mentioned, we do our unit test, acceptance tests, and like canary tests, as I'm sure most of you all do. But we also do fuzziness and correctness test. What that means is, especially for our query capabilities, given PromQL supports wide a range of queries, if we are making any changes on our query path, we want to make sure that we are not introducing regressions on the query logic. In order to test that, what we do is we generate a bunch of random queries, and then when we deploy our changes to our gamma environment, we look at the results from Cortex, and then we also have a vanilla Prometheus instance running in our gamma environment that we compare the results to. If things are looking fine, we wait a little bit to gain confidence and release our changes. We also do fault injection between production waves. What that means is we basically test the resiliency mechanisms that we have in our system to test such as like against AZ impairment. So what happens inside a cell's deployment? That's when we deploy our Cortex images to our Kubernetes cluster. So a quick word about our architecture is that even though, as Alan mentioned, we can tolerate disruption in a single AZ, the system incurs a small downtime when two ingesters are down from multiple AZs. So how is this relevant to our deployment process? So we have a stateful set when we are for our ingesters when we are deploying Cortex. So pod disruption budget doesn't necessarily take zone into account when it's replacing pods. So if we are taking if we are replacing two pods, it's highly likely that we are going to be taking two pods from different AZs, and we don't want to cause any impact to our customers. So we introduced zone-aware controllers. Zone-aware controllers are open sourced, and you can use that in your projects if you have stateful sets and relying on multiple AZs. How that works is that, as you can see from the top left graph, we start replacing nodes in one AZ. We start small. We take one, and then we take two, and then we take four. We exponentially grow, and then once that AZ's deployment finishes, we move on to the next AZ. So this process speeds up our deployment by a huge margin. So what happens after we deploy all of this complexity? The gray failures can happen. If you are operating your service that relies on tens of thousands of hosts, any number of those hosts can go down at any time. We do our health checks, but there are gray failures that cannot be necessarily detected through health checks. So we do host health monitoring to be able to detect gray failures such as network and disk failures. We use multiple signals to determine if a host needs replacement, such as 5xx count or latency. We replace the node even if we get a false negative signal to not disrupt the service at all. You can use this mechanism to way away from an AZ in case of AZ failures if you'd like. As we are looking at our deployments, we also noticed that Karpenter project for Kubernetes is taking off, and we are in the process of moving to Karpenter. Karpenter provides us a better transparency and debuggability during deployments, which helps speeding up the deployments. On our observations, we also noticed that Karpenter provides faster scaling characteristics. And in operating global scale, you can have capacity constraints on the hosts that you are running your service, host types specifically. So with Karpenter, we can pick multiple instance types to run our service, and then we do not get any capacity constraints. So what's next for Cortex? We are as I mentioned before, we are tolerant across single AZ outages. But however, due to how we shard our data, we incur a short, small impact when two ingesters are down from two different AZs because of how the series are assigned to ingesters. What we are thinking of is introducing a new concept called partitions. Instead of directly assigning series into ingesters, we are going to assign series to partitions, and the partitions will be assigned to ingesters. So how does this work in theory? With the introduction of partitions, we are more resilient towards multiple ingesters going down across multiple AZs. Notice that the customer or any time series is not going to have any impact even if more than 3 ingesters are down from 3 different AZs. The only downside is we can only have impact if 2 ingesters are down from the same partition, but which is less likely to happen compared to our previous state. That being said, one of the next things we are working on is we are exploring Parquet format for our long-term storage, working with the upstream community as well as Thanos maintainers. This will keep the same query performance, but with further optimizations, we can improve query performance. But the main focus of this effort is to be able to reduce the operational toil introduced by store gateways and reduce the infrastructure needed to run Cortex. So that's it for today. If you are interested in learning more about our improvements and how to run Cortex and what's next, please feel free to attend the talks that our maintainers are going to give on Friday. You can also find us in Cortex and OpenSearch booths, as well as reach out to us in CNCF channels. Thank you.